Multinomial Logit, which is one of the choice models used very frequently in electoral research. So as to give you a general idea of choice models in political science, or in econometrics rather, there's three varieties of choice models out there. One variety of choice model that is out there is, and then they all have a long history. One variety that is out there is the loose type models, and that's where multinomial logit fits. And these loose type models, they make a fairly strong assumption that goes under the name IIA assumption, independence of irrelevant alternatives. Basically what this means is the following. Imagine that, that we live in a three-party world. And there are two big parties and there's a small party, and I look at the ratio of the probabilities of the first big party, we voted for the first big party, and we voted for the second big party. Then independence of irrelevant alternatives says that this ratio of probabilities with party C in the choice set is the same as the ratio of probabilities without C. So should C suddenly cease to exist, it doesn't actually affect the relative probability of belonging to party A and party B. That's a strong assumption. But that's the assumption we're going to be making today. And then to bypass that assumption, if you look at a second class of choice models that go back to Thurston, they are actually quite old. They go back to the 1920s. And they don't make the IIA assumption. They fully relax it. This sort of notion of these Thurston type models, that is encapsulated, for example, in something known as the multinomial probit model that you may have heard about. And then there's a third set which I sometimes associate with the psychologist Amos Tversky. They are basically sequential models with a partial relaxation of IIA. Now these sequential models with a partial relaxation in IIA have relatively little legacy in political science. Very few people use them. There's only a handful of articles. I think they're actually in some ways the most interesting of the three types. We will not consider those either because the multi-level extension is very complicated. I will not consider the multinomial probit because even without the multi-level extension, that model is very complicated to estimate. And again, talking about your corner solutions, which we saw yesterday, there are papers published by prominent people using multinomial probit that have corner solutions reported, so not uncommon. So we're going to focus on the loose type models. They are the most simple of the three types, and still actually I would say the most widely used in electoral research, despite this IIA assumption, which is really a fairly unrealistic assumption in many cases. What all of these three types have in common is that they are models that assume some variety of utility maximization. And that's the intuition I'm going to use to derive the single level model. So to give you an example, a simple example, imagine we consider vote choice in Britain, but not just did you vote for Labour or another party, but let's focus on vote choice between conservatives, Labour, and Liberal Democrats. Now, of course, you could extend that to other parties, but the general ideas will remain the same, so I'm going to stick with this piece. We want to model the vote probability for each party. In the 2001 elections, for some individual, what was his or her probability of voting for conservatives? What was his or her probability of voting for Labour? What was his or her probability of voting for the Democrats? And here is how the probabilistic choice models approach that question of the choice probabilities. They also, in a sense, again, postulate a latent variable, but they're a little bit more precise about what that latent variable means. They typically, at least economists and psychologists, will give that latent variable an utility interpretation. So they say, you have some person in Britain, and this person experiences a certain utility towards Labour, a certain utility towards the Conservatives, a certain utility towards the Liberal Democrats. And therefore, we can characterize, individualize utility towards party M as UIM. We don't actually observe this UIM. The same as what we have with ordered logit and logit with a Y star, which we don't observe either. We break this UIM down into two components, a systematic component VIM, which I am going to model out later. I'm going to wait on that for a little while, but I'm going to get there eventually. And an error component epsilon IM. And you think about this as in a variety of ways. When you think about it, first of all, we say, well, VIM are the factors that we as a researcher are aware of influence someone's utility. So in a typical electoral setting, those might be things like party identification, there may be things like issue preferences, there may be things like candidate attractiveness, things like that. Epsilon IM is all of the stuff that we as researchers are not aware of because we never thought of them being things that might influence the utility, or because we lack the measures. They are just things we have measured in our data. So that's one interpretation of this epsilon. So to say, well, it's the researcher's ignorance. You might also give a bit more of a psychological interpretation to it and say, well, maybe even the decision maker, maybe even the voter, him or herself, is not fully aware of all the things that influence their utility towards, say, Labour. There are certain things they are aware of that influence that utility, and other things they may not be aware of. You want to be Freudian about it because they sort of reside deep in the unconscious of the individual. Things went terribly wrong during toilet training, and because of this, the person has a paranoid fear of left-wing parties, they will never be able to tell you that they have that, but it influences their utility. Doesn't really matter. We have this random component epsilon that, in addition to what we know as researcher, influences their utility. And then we have this utility maximization postulate that I already mentioned, which says a person votes for the party that gives the highest utility. So person I will vote for party M if the utility of party M for that individual is greater than the utility for any then other party in the choice set. So in our example, person I is expected to vote for the conservatives if, and only if, the utility of that individual for the conservatives, party 1, exceeds the utility of that individual towards Labour, party 2, and at the same time, the utility of the individual for the conservatives exceeds the utility for party 3, the Liberal Democrats. And taking advantage of this formulation of these utilities, the V plus epsilon formulation, you can also formulate that a little bit differently as person I is expected to vote for the conservatives if the random component associated with Labour is less than the difference in the systematic utilities between the conservatives and Labour, plus the error associated with the utility for the conservatives, and at the same time, the random component associated with the utility for the Liberal Democrats is less than the systematic utility for conservatives minus the systematic utility for the Liberal Democrats plus the random component of the utility for the conservatives. You see actually here some important property of this choice mechanism. You sort of ignore the errors for a moment. You see that what's critical are the utility, the systematic utility differences. It's not about the absolute utilities as such. It's about how much more do I prefer, how much more utility do I have for the conservatives as opposed to Labour? How much more do I have for conservatives as opposed to Liberal Democrats? Now, then we need to come up with a choice probability, and the choice probability is basically the probability of utility IM exceeding that of all other alternatives. And I'm missing a parenthesis here. It's basically the probability that epsilon for some other alternative is less than the systematic utility difference plus the epsilon associated with the alternative I'm interested in for all of the other alternatives. And now we have to make some assumptions, and this is where the difference between these three models types of models is starting to come in full force. Because we need to make some assumptions about the distribution of the epsilons to actually work out what this probability is. And the key thing that these loose models assume is that these errors, epsilon IP and epsilon IM, are independent from one another. That is really what drives this IIA. These epsilons are independent, which means to say that if my toilet training makes me feel less utility for Labour, that has no bearing on the utility I feel for the Conservatives or the utility I feel for the Liberal Democrats. We could, of course, make an argument that maybe if your toiletry makes you authoritarian, then maybe the Democrats suffer too from that. That would introduce a correlation between the absolutes. But we rule that out here. Basic computationally much simpler, because what you would have to do in a multinomial probit model is to then say, well, these epsilons, they're all related to each other. So say we have three alternatives, we have three epsilons. Let's impose a trivariate normal distribution with a covariance matrix on this whole thing. That's much more complicated. In fact, when you wanted to extend that to a multi-level analysis, the integration problem becomes enormous, because to get the probabilities in the trivariate normal, you already have to integrate. Now you have to integrate a bunch more to get rid of the deltas, and it gets basically messy. I have not seen anyone outside of the Bayesian framework trying to do this. So we stick away, stay with the simple assumption here. And then the other assumption we make about the errors is that they follow the Gumbel distribution. It's not so critical, but it turns out, and this is a very tedious thing to show, but if you do half an hour worth of math, you come down to this expression at the bottom. Now, Luce presented this expression in the 1950s without doing all the math. He intuited that it looks this way. Daniel McFadden, who is sort of the Nobel Prize winning econometrician or choice models, does it with all the math. And try to reconstruct his work. It will take you a little while. Here's where you end up. E raised to the power systematic utility for alternative M over the sum of E raised to the power systematic utility of all of the alternatives in the set. So the probability of someone voting for the conservatives would be E raised to the power V1 over E raised to the power V1 plus E raised to the power V2 plus E raised to the power V3. That's the Luce model. Now, we want to model this out. And I'm going to model this out in terms of a single predictor for now, because again, I want to keep it simple. And so I'm introducing a single predictor and a constant to account for the systematic utility that someone might feel for a party. So X could be, for example, the issue distance to the party, or X more either could be your left-right self-placement, because it's an attribute of the decision maker that we're introducing here. So say this is your left-right self-placement, and this could be a constant. And you see that both the effect of left-right self-placement and the effect of the constant are allowed to vary across alternatives. Basically, what you're saying is, well, ideology may be less relevant for some parties than for other parties in terms of determining their utility. And the fact that constant varies across the alternatives could pick up something like party valence. Maybe the conservatives are really doing terrible in 2001, which they were. People just don't think that the party is ready for government, regardless of whether they feel close or not close to the party. So you could then just substitute that into this model, and then you have what's known as the Multinomial Logit model. except we need to do one additional thing, because this model, as I presented it here, unfortunately is not identified. Why is it not identified? Well, there are 3 V components we like to estimate, but how many unique choice probabilities do I have when I have 3 parties? We know that these choice probabilities have to add up to 1 if the parties are mutually exclusive and exhaustive of the set we're considering. So that means we only have 2 unique probabilities. We cannot estimate 3 V's. It's impossible. And that means we have to get rid of one of the V's. How would we do that? For one of the alternatives, we set beta 0 and beta 1 equal to 0. That then becomes the so-called baseline alternative. And you can say, well, that seems like a crazy thing to do because why would you arbitrarily fix the utility for, say, the conservatives to 0? But here is what comes to our rescue, is what I already mentioned earlier. The fact that it's actually not the absolute utilities that matter, but the utility differences. It doesn't really matter if I say this is 0, because it's not the absolute value of V1 that matters, but its relative distance to V2 or to V3. So we can actually make this baseline thing without any difficulties. But before I go to the multi-level extension, let me just show you simply how in Stata you would then estimate this. So and it's really quite simple, because you essentially just type M-logit for multinomial logit. Tri-vote is the trichotomous vote here. Left-right underscore S is left-right self-placement, and I have middle and working class dummies. And then here is the set of estimates that I obtain. Stata has this preference to use as the baseline category that category that was selected most frequently, which in this case is layer 2. It doesn't really matter how you do this. You can pick any baseline category. If you would like conservatives to be the baseline, then the only thing that you have had to change in the syntax that I just ran is to say conservatives G1. I think that works. And now the conservatives have become baseline. It doesn't matter, again, because it's not the absolute utilities that matter, but the utility differences. And what we then see in this setup, where we now have made conservatives the baseline, is that we indeed get different coefficients for left, right, self-placement, for middle, for working, and for the constant. When the difference for left, right, self-placement is actually not very large, I imagine if we actually impose the constraint that this effect and this effect are the same, it would actually not lead to a terribly fitting model. But it basically suggests always that we sort of compare voting for Labour to voting for the Conservatives. You get a negative effect for left-right self-placement. That means as people move to the right, their inclination vote for labor as compared to conservatives decreases. The same with liberal Democrats. We see that middle class voters slightly, a slight tendency, it's only marginally significant, to be less inclined to vote for labor than conservatives. There's no effect for middle class for liberal Democrats. For working class, you see an effect. Working class people are more inclined to vote for labor than conservatives. They are not more inclined to vote for the liberal Democrats compared to the conservatives. And then we see constants. Now that's the basic setup that we have. We can again interpret this in terms of odds ratios. We can interpret it in terms of predicted probabilities. If we just exponentiate these coefficients that are given to us in the output, then we get the odds ratios relative to the baseline category, which is voting for the conservatives. So what we actually end up getting are odds ratios like lab to conservative, them to conservative. And that is just e raised to the power of these coefficients that we can give you factor changes in odds. And actually, what I tend to do with these kinds of models is there is a package that Scott Long has written. It's called sPost. And one of the commands in sPost is the listcof command. And this listcof command will give you all of the relevant odds, factor changes in the odds. So you have to install this. It's not part of the standard installation for Stata, but here is when you type the command, what you get, and I'm only going to focus here on the on what happens to the effect of left-right self-placement. This is just repeating a set of estimates. This is actually then the factor changes. And here's how you read this. This is the party whose probability would appear in the numerator here. This is the party whose probability would appear in the denominator. So 2 versus 3 means the probability of voting for labor over the probability of voting for the liberal Democrats. And you see that the factor change there is basically 1. But that is no surprise because I actually already told you the effect of left-right for labor and for liberal Democrats is almost indistinguishable. So it's no surprise that if you increase the unit on left-right, it doesn't really help to discriminate between those two parties. When you compare, though, voting for labor and voting for the conservatives, that's the second line, then you see that the factor change is 0.6. So 1 unit move to the right of the ideological spectrum decreases the odds of voting for labor relative to the conservatives by a factor of 0.6. And then here is 3 versus 2 is of course no much different than 2 versus 3. This factor change of 1.0056 is just 1 over this factor change, 2.994. we have then 3 versus 1, the Liberal Democrats versus the Conservatives. There you see that the factor change is about 0.6 again. So if you say, well, someone becomes 1 unit more conservative on the ideological scale, then the odds of that person voting for the Liberal Democrats compared to the Conservatives shrink by a factor of 0.6. And then the last comparisons are then the Conservatives relative to Labor and the Liberal Democrats, but those are again not unique because we already have seen the effects in another cell. So that's what you would do with the odds ratio. Predicted probabilities, you can also obtain, of course, you can figure out what are the predicted probabilities of voting for Labor versus voting for the Conservatives. For example, if I want to know what happens to these predicted probabilities, I can use another command in this sPost, which is PR value, no, PR change, sorry. And there, what you will see is the following pattern. So it's PR change. PR value is something else. If I change, for example, left-right self-placement from its minimum value, which is extreme left, to its maximum value, which is extreme right, the probability of voting for the Conservatives increases by 0.74, of voting for Labor decreases by 0.54, and of voting for the Liberal Democrats increases by 0.20. Holding all else at the mean. So in this case, holding all else at the mean is a little crazy because the other predictors in the model are working class, middle class, and what you do when you hold them at the mean is essentially saying, well, what is the mean of a proportion? The mean of a dichotomous variable is the proportion of people who are working class and the proportion of people who are middle class. But that's what it does anyways. So that's the setup here. And now I want to say, okay, let's generalize this. Because, again, the data structure that we're dealing with here allows me to actually consider constituencies. And this is a natural second level unit when it comes to electoral choice, because we know that the fortunes of political parties vary across districts. There are conservative districts, there are labor districts, there are districts that go for Liberal Democrats, so we can take that into consideration. The simplest way to take that into consideration is to turn this model I just showed you into a random intercept model. To say we have this beta 0 that is associated with the different alternatives, but in addition to having that beta 0, there's a random component that is due to the different districts that can come into play. So voters and estimating constituencies, therefore Yij is voter I's choice in constituency J. The systematic utility component now is Vijm. Voter I's in district J's utility towards alternative M. and we want to allow the intercept to vary in that component, and we can do that by adding to the model I had before this component delta 0j. We could make this actually a lot more complicated, although you can run into identification issues quite quickly, because what you could do is to say, well, this delta 0j varies also from one alternative to the next. You could do that, but you may end up with some utility, with some problems getting into converge. So we won't do that here. Just have this delta 0j. So you can think of this beta 0m component and this delta 0j component in conjunction as being some sort of moving around of the party fortune in different districts. So imagine that we have a situation where the Labor Party really does poorly in a district. Then we have beta 0 for the Labor Party, and then we may have just a very negative delta 0j in that particular district. So how do we estimate this? The syntax for this kind of model is really not that difficult. What we need to do is to actually run the following command. And this looks very similar to what we've been doing. glam, the command, dependent variable predictors, identification of the level 2 unit. And then the only thing that really changes relative to what I've done before is the link function. The link function here is now an M logit for multinomial logit rather than O logit or logit, which is what we were talking about earlier. I left the number of integration points at 10 just to speed things up a bit. If I would really do this for research, I would probably increase it to 30. Adapt, because we're doing adaptive quadrature. So I will run this. And as usual, it takes a bit of time. And that's why I lowered the integration points, because otherwise it takes even more time. But it converges fairly well. This is not that difficult of a model to estimate. It gets much more complicated when you allow effects to vary. So we're done with the numerical integration. Now we start with the optimization of the likelihood. Warning. Not too worried when it happens that early, it's no big deal. And we're done. Condition number is again something I would look at, not too bad. Again, I mean, with this condition number, I didn't really explain what it is, but because it gets mathematically complicated, but it basically is an indicator of convergence. And you just start worrying about it when it gets in the thousands. So in the hundreds, I wouldn't even worry about it. This certainly is not something to worry about. And then what you get is basically something that is very similar to what we had before. I could have also set the baseline category here, but this glam command by default takes the first value of the dependent variable and makes that the baseline, which is what I did before. And then we have here the effects of the different predictors, which are allowed to vary across the alternatives. And then the only other thing that is added here that you would not see in a normal multinomial model is an estimate of the variance of delta 0. The variance is 0.32 with a standard error of 0.12. And again, I don't think this is something you should do as the ultimate test, but you can always sort of see, is this significant or not, by just taking the ratio of the estimate over the standard error and asking yourself, is it greater than 1.96? And this ratio is about 3, is clearly greater than 1.96. Seems to suggest we have really significant variation in the intercept. You can also test this much more formally, and again, it's probably useful to show you this again. We can just basically do the likelihood ratio test. So I can store the results here, and then I can repeat the analysis with a multinomial logit, and then I can do the likelihood ratio test here, LI test, full, and again you have to force data to do this test for you, but you see it really is clearly significant. I mean, this model is essentially the same as saying this variance of delta 0 is 0. And that in turn is the same as saying we don't need the delta zeros. There is no variation across polynesters. Well, does this model fit the data worse than the model I estimated that allows for these deltas? This is the indication. We get a likelihood ratio chi-square based on the deviance of this model and the deviance of the previous model, that's equal to 16.9. And when you refer that to a chi-square distribution with 1 degree of freedom, you get a probability that is 0. But actually, you have to have this probability, because we're doing a one-tailed test. It's really 0. There might still have something happening in the fifth decimal here, but when you divide it, you can just say it's nothing. So we really have evidence here that the intercept varies. Now, how do we interpret this? Now, here we could go do the same thing that we did with the ordered logit and the logit itself. We could go back to the analysis of the random intercept model and start by saying, let's just take the logit, that is the natural logarithm of this, which is then just the linear function that we see here. The effect of left-right self-placement for labor, the effect of middle for labor, the effect of working for labor, the constant for labor. And then we average out all of the level 2 components so we don't have to worry about it, and then we can just calculate loss ratios based on these estimates. What I'm going to do is a little bit different. I want to deal with predicted probabilities, and the predicted probabilities that I want to deal with are predicted probabilities of two kinds again, because that doesn't change across these models. We can do marginal predicted probabilities, and we can do conditional predicted probabilities. I'll start with the marginal predicted probabilities, where you say, let's calculate the probability of voting for the conservatives, the probability of voting for Labor, the probability of voting for the Liberal Democrats, ignoring, that is, averaging out the random coupons. And you do that exactly the same way as in any of the other models we've seen today. And the syntax is again also very similar to what we saw today. And I have that here. So we start by getting the marginal probabilities, and what I do is I say GLA pred, and then I give names. MCOM for marginal probability conservatives, MLAB for marginal laborers, etc. Mu, because we're again predicting a probability. Marginal, because we want to average out the random intercepts. And then we just have to indicate for what outcome we want to calculate this. So 1, 2, or 3. And that's what we get here. So I can run that. And then I could, for example, if I wanted to, plot the predicted probabilities as a function of left-right self-placement. Let's say we do that for working class people. So I set middle equal to 0 and working equal to 1. And again, I will send these syntax files to Fiona, and then she can distribute them to you. I'll do that later today or tomorrow. And then here we see the predicted probability, the marginal predicted probability as a function of left-right self-placement. And we see that keep doing this. So I'm not trying to click just show with my finger. So see that as you move from the left here 0 to the right here 10, that you see this precipitous decline in the probability of voting Labor, precipitous increase in the probability of voting for the Conservatives, and a somewhat flat relationship for Liberal Democrats. I mean, there is some decline there, but it's not as much. It's also interesting to note that the gap between the probability of voting for Labor and Conservatives for the very left people is much, much higher than the gap for very conservative people. But that may be a function of the fact that we're looking at working class individuals here. So you might want to depict this picture again also for middle class voters to get a fuller impression of what's going on. Again, we did not let the effect of left-right vary here. The only thing that we let vary was the intercept, and we got rid of that variation in creating this picture. So this is just the marginal predictabilities. Now, it is also possible that we want to actually include these level 1 errors, because I might want to be able to say something about the relationship between left and right and vote probabilities, vote choice, in a particular polling district. What I need to do then is I need to calculate conditional probabilities. And again, that's just a very slight variation on the syntax that I just used, because the only thing that changes there is that I get rid of the option marginal. And so I may want to depict this again for, say, Dundee West and Beaconsfield, and then this syntax will get you the little graphs. Oh, there's a reason I did not do that. Do not do that particular graph. It's actually good that I did, because it shows you a feature of GLM that I never discussed yet. Here is Dundee West. There was Dundee West, and it's gone again. And in Dundee West, you see sort of the same relationship that you already saw, but possibly a little bit more pronounced yet. This gap here is now non-existent. But overall, the pattern is, of course, very similar. And then there's nothing for Beaconsfield. Well, that may be not because people in Beaconsfield didn't vote, but if there is no variation on the dependent variable, then actually GLM doesn't calculate the predicted probabilities. Or it may also be in this case that there are just no working class people in Beaconsfield. That's why it didn't calculate predicted probabilities. But that's sort of one of the features, that there's no variation in the in the outcome. Everyone votes for the same party. Then the problem that occurs is that GLM just doesn't compute the predicted probabilities. So again, you may not want to do this for all 127 districts in the data. You may again want to say, well, okay, let's look at the distribution of the empirical base estimates of the deltas and pick the lowest delta, the highest delta, and a couple of intermediate values to sort of show you what happens at representative values of this random intercept. That would be a better way to depict. Then you wouldn't have to draw 127 graphs like this, but only, say, 4 or 5 of them. That's much better. That would be telling the story just as well. So that's then the thing you would want to look into. Now, all we've done so far is actually do a random intercept model. You could, of course, easily extend this. And then say, for example, okay, that's the last thing I will show you. What happens if I, for example, let the effective class vary? So, So our class is captured here in two dummy variables, middle and working. So I need to start by specifying an equation for the intercept, an equation for the first slope, which I say is associated with middle class, a equation for the second slope, which is associated with working class, and then I will paste Logit, and make that into 15. Then let me then add the other things that I need. The number of random effects now is 3. The equations, let's see, IQS. The equations are now inter slope 1 and slope 2. And let me ask for therapy quadrature. Let me see if this works, because yesterday I was having a terrible time with this. This is the first time I try this, so no guarantee that it actually will run. Okay. I'm asking for too many integration points, because the dimension here is greater than 2, which means because we have more than 2 random effects. So I need to change that. So we will turn this then into 5. And then 2. That may run very slow. We can see if there is evidence that class-based volume varies across distance. That's basically what the point of this exercise is. Now, while we're waiting for this to do something, let me say a little bit about the limitations of these models in electoral research. It works in the British context, at least the way I define all choice, because the choice set is the same everywhere. Everywhere voters can vote for Labour, Conservatives, and Democrats. Now, if you do cross-national research, unfortunately, it gets a little bit complicated because the choice sets vary from country to country. The number of alternatives varies, but also fundamentally the meaning of the alternatives varies. And it makes it incredibly difficult to run a multinomial logic model, because basically, to make this model work, the number of alternatives and the meaning of the alternatives has to be the same. The number of alternatives has to be the same for technical reasons. The meaning of the alternatives has to be the same for reasons of measurement equivalence. And so you cannot really generalize this easily to multi-country electoral studies. And when you have that kind of problem, that is, you want to run something across countries that is a choice model, what I would do is to probably simplify this somehow to a dichotomy and do something like voting for the government, voting against the government. You could make it more complicated than that. You could say voting for the government, voting for an extreme left-wing non-government party, voting for a right-wing non-government party. That's not the problem. The problem is really that you keep the number of alternatives the same and that they relatively have the same meaning across different contexts. That's sort of what I would like, what I would do in that situation. I don't think there is an easy way to generalize these models. There is some interesting literature developing more generally in choice, on choice behavior that deals with this issue because there are, of course, cases where parties just don't compete. And in Japan, ostensibly, this happens quite frequently, that parties don't compete in certain districts. And so there is actually a paper, I think it is likely to be published soon, of one of some people at Princeton University that deals with that particular issue. I myself have been working on these models in the third category, these Tversky type models, by doing some work on choice sets, and there's some development there as well, but none of it is multi-level yet. So that may or may not happen because it's quite complicated. Another comment I want to make, and this is actually briefly mentioned in the reading that I assigned for this topic, is that it may be possible in a multi-level setting to circumvent this IIA assumption. But very specific requirements have to be met in order to get that identified. And you basically have to have quite a bit of additional data to make that identifiable thing. It sort of amounts to adding error components of two kinds. Error components that really deal with the with the dependencies between the alternatives, that almost becomes the second level, and then the third level might become like the polling district. It is not clear how easy it is to get that identified. I'm a little skeptical. I've tried it myself, and it doesn't seem to work. This is not a trivial estimation problem, apparently. I'm sort of surprised we don't get more warnings at the moment. So it seems to be quite happy, even though it's slow. We have no... The other kind of warning that you might actually get sometimes there, in addition to this backup warning, is a message, not concave. And not concave means that in the optimization it has hit a point in the log likelihood that is flat. Then it can't move forward, or it sort of works its way out of the problem. Again, it's a message you don't worry about if it comes in the beginning. If it comes in the last iteration, don't trust the results. But we have something. So let's see what we have and whether it makes any sense. So this is the variance in the effect of being middle class. This seems to actually vary a little bit from just eyeballing the ratio of this variance component to this standard error. This would be, no, this would actually, sorry, I'm reversing this in my head because this is actually the intercept. I'm always, in statites, if state estimates something, the constant is always the last thing, but I specified it as the first thing, so this is actually the variation intercept. That seems significant. But then here we have the variation as a result of middle of class. Here's the variation, and this is the middle class, and this is working class. And eyeballing those ratios, there's not much going on. So, and what worries me a little bit, although it's not terrible, but this is pretty high for correlation between the intercept and the slope. This one I would actually expect to be fairly sizable because this is the effect of middle class and the effect of working class, and since they basically both measures of rate of class, I would expect these effects to be high. But that just to show you that there doesn't seem to be much difference in the effect of class across constituencies. So that brings me to the end. There are lots of other models you can estimate as multi-level models, but I don't think they're as useful in electoral and public opinion research, so that's why I decided to leave them out. So let me just recapitulate sort of as an overview of what we've done the last day and a half, which is actually quite a bit. I know Kelvin Jones teaches a multi-level class in Essex, and he gets to Logit, where we sort of ended this morning in 2 weeks. You said we had to deal with much more than that in 1.5 days. So maybe an overview is not that bad to see the trees a bit again. So the starting point here is that multi-level data structures offer lots of opportunities for research. That's why I think we've seen in electoral research sort of the movement towards comparative electoral surveys. A lot of these things have been established, and I think it is for a very simple reason. One, that we can do a bunch of national election studies, but it would never allow us to see similarities and differences across political systems, and it would never allow us to bring into the analysis institutional explanations, because institutional features don't generally vary within a country. There's some exceptions to that, but often they don't, and they do vary cross-nationally. Things like the size of the party system, the state of the economy, the nature of the electoral system, you can add to that very easily. And this is why we like to have these multi-level data structures. That's why they're so prominent. But they come at a price. And the price that you have to pay is that they also contain some traps, some statistical traps that you can walk into. Some of these traps having to do with model specification, with bias, which are really in the end then again theoretical traps. What is a proper model to bring together, say, data at the individual level and data at the country level? Some of them traps having to do really with the dependencies across observations that are common in multi-level data structures. just like you would expect a time series to have some autocorrelation, you would expect a multi-level data set to display some degree of clustering. And the degree of clustering that you will see is very likely to be positive clustering, positive interclass correlation, which means that if you just go out and run an ordinarily scarce regression, you're going to get incorrect standard errors. Now, there are ways around it. In a linear model, it's actually fairly easy to get around that. You can do cluster corrected standard errors. You don't have to worry too much about anything else. But these solutions don't generalize very easily to other kinds of models. When you get to nonlinear models, like the Logit models we discussed yesterday afternoon and today, these solutions based on cluster corrected standard errors don't really do the job. Contrary to what Status seems to think, most statisticians would argue that they only address part of the problem and not the most important part of the problem. And that's why we're searching for a method that really can allow us to explore the rich features of multi-level data structures at the same time that we can address these statistical issues, and multi-level analysis is actually a good way to go there. But I think there are some pitfalls, and I also think that the political science community hasn't generally really taken good advantage of all the things that multi-level analysis has to offer. The pitfalls are the ones that I talked about last afternoon. We have to be pretty good at specifying theories. Again, that's the specification issue. We have to also consider fairly seriously, at least in a classical frequentist framework, the sample size of the numbers of level 2 units, and the number of clusters. And we have to also take seriously measurement, in particular measurement equivalence, which unfortunately I think is sort of not something that political scientists do a lot of. I think the sociology world is actually much better at that than the political science world. So those are the pitfalls, and I think you just have to be aware of them. I don't think that they're an argument against doing multi-level analysis. I think they're an argument to do better multi-level analysis. And even if you were to not do multi-level analysis, things like model specification and measurement equivalence don't go away. They will always be there. Here is where I think the political science community really has not fully explored the rich features of multi-level analysis. What I see as a reviewer, a frequent reviewer of papers that use multi-level analysis is this. Political scientists run random intercept models, barely bother to report the variance component associated with those random intercepts, sometimes actually don't report the variance component, and they will only interpret the fixed effects. Well, you just used a very powerful tool to get a minimal degree of information. First of all, I think you want to, at a minimum, report all the variance components and maybe use them to do things like a computation of an R squared, to say, okay, I've added this level 2 covariance, see what happens to the variance component. How much do I really explain with this level 2 covariate in terms of variation in the slopes or the intercepts? Separately, why don't you just fix the effects discussion, because you can do much more than that. I mean, the whole point of doing multi-level analysis, especially when you believe there's causal heterogeneity, is to say, maybe the relationship in the Netherlands looks different than it looks in Turkey. Well, why not actually then show that? Why say, let's pretend we have the average individual in the average level 2 units, so we can get rid of all of the random components that we just did such a careful job introducing in our multi-level analysis, and just interpret the fixed effects. Why not also say, here is what the effect looks like in Turkey, here is what it looks like in the Netherlands. That is, I think, what people ought to do much more. And again, I think you could do that already with a random intercept model. It becomes particularly interesting with random slope models. And that is the other place where I think people ought to really start thinking seriously about multi-level set analysis. What they say, well, let's also think seriously about causal heterogeneity. This is, I think, a very different model of science ultimately. Like I already mentioned yesterday, it's a condition-seeking model of science. It doesn't say, is there a relationship or not? Which I would argue is sort of the first step of scientific progress. And the more mature scientific progress is to say, well, under what circumstances is there a relationship? Under what circumstances is it positive? Under what circumstances is it negative? But that's the causal heterogeneity business. And all of this you can get in a basic program like Stata with GLAM. And you can report that. I would encourage you to report it graphically. I think it tells a lot more than a bunch of words. And all of this, I think, would really help to explore all of these rich features that these multi-level data sets have. And we have lots of them. And they're not going away because rightfully, I think, scholars in more than just electoral research, but especially in electoral research, have decided that the comparative dimension of electoral behavior is actually a very interesting dimension. And of course, we haven't talked about longitudinal data that much, but the longitudinal dimension we can also model out, and I think that's another area where I think there's a lot of room for progress. So I'll end on those comments, and I hope you are not too overwhelmed after a day and a half of pretty intense multi-level analysis. Like I said yesterday, if you have questions, if somewhere down the line you say, well, I don't understand this, I thought I understood it, but I don't, or you have some specific problems in your research, feel free to send an email. Keep in mind that I am sometimes slow responding to my emails, so if you don't hear it from me in a day, that doesn't mean that I didn't see your message, but it's more likely that I decided not to answer my email that day. But then, good luck for those of you who are actually want to use this stuff, and also good luck getting through the remaining half days time series, which is yet another world of ideas. Good.
Would you be willing to take one or two more questions?
Yeah.
If anybody has, because anybody else have a question? I have a sort of a very practical question, and a bit motivated by some of the questions that came up and some of the issues that you addressed about Bayesian approaches to multi-level analysis. And as I do with anything, fear. My fear is that now, anytime anything's sent out for review, where it uses and justifies a multi-level analysis that doesn't use a Bayesian approach, that a reviewer will say, oh, well, now we all know that a Bayesian approach is the best and most innovative and way to address some of these concerns. And you very much suggested, I think, that it doesn't address all of the concerns, and that we're quite okay to proceed in, with the methods that you used, or the approaches you used. Is there a way that we could, those of us who are expecting responses like this, respond to the news?
Yeah, I think so. But I think the issue, the biggest issue, I think, that speaks in favor of a Bayesian approach is an issue of the sample size requirements. I think that comes up. And the Bayesians, there is some evidence out of the Bayesian world to suggest that the Bayesian setup solves that problem to some extent. And I have seen some rather dramatic examples, like Andy Gelman has no problems estimating a multi-level model where he has 6 level 2 units. And of course, Andy Gelman is a statistician as well as a political scientist, so he probably will never be called on it because people respect his view. I get a little skeptical myself. I think what we do in the Bayesian setup is we do help the data a little bit by providing a prior. We're not relying entirely on the data, but relying also a bit on the prior. But the priors that we typically specify, and I think the only priors that we really can get away with in political science are uninformed priors. That is to say, what you could do, for example, if you're worried about a variance component, is you could specify a prior, and typically it would be something like an inverse gamma distribution, but you would give it an enormous variance, so that you basically say, well, it could really be any variance. That's sort of the idea. And if you then look at what a Bayesian posterior is, then the Bayesian posterior gives all of the weight, practically all of the weight, to the likelihood anyways. And this prior has only a little bit of a role to play. Now, sometimes it's enough to get rid of small sample bias. But I think if you have just 6 level 2 units, I get the feeling that to get this all organized, to really get the information, you would have to make the prior significantly more informative to really make it help you out. And I don't think informative priors fly well in political science. I know Jeff Gill is saying that political scientists are just Bayesians of convenience because the only thing we ever use are uninformed priors, but I don't think we can get away with anything else because rightfully reviewers will say, well, aren't you just getting out what you put in? And there's some answers to that. But I think what is important is to say, okay, that is really the only issue where I think the Bayesian setup offers a significant advantage. And there is some evidence that you can make it work in small samples, but some of that is based on a limited number of simulation studies, and I'm always a little skeptical of simulation studies because they won't always quite capture the situation that we face in our actual research. If you want to defend yourself, then I think what you need to do is say there is an alternative approach that has been shown to work very well. The issue is likely to come up with these nonlinear models where the Bayesian approach also will work very well. You just say, well, there is evidence that these numerical integration methods actually get it right, and there's a paper showing that. I will send the site so you can quote it. It's also simulation-based, but they do it simulation-based, you also do it simulation-based too. So, and that you then say, well, I mean, there's no significant evidence of bias, and I think that is then the best defense. The fortunate thing is, I think, although the number of Bayesians in political science is rising, it's still a minority. It's a vocal minority, but I think they've penetrated selectively in the discipline. So if you do anything item response theory these days, I think you're much more likely to get the criticism that you should do with Bayesian than when you do multi-level, because most people do multi-level work in comparative research. There, I think Bayesians is still a minority, so that will help. I mean, I think it's useful to think of Bayesianism as an alternative. I think it has a lot of advantages. What I sort of don't like is the Bayesians sort of declaring that their way is the only way, and that seems to be an exaggerated claim, I think. It's with everything. If you have a badly specified model, Bayes' theorem is not going to rescue you. And if you have bad data, the same is true. So, I mean, some of the problems you have in multi-level analysis just don't go away with Bayes. And the other argument I would have is that sometimes it becomes quite non-transparent. It's not so bad in multi-level analysis, but I was talking with Chris about some stuff that Bayesians are doing with pooled time series. They have so many priors going on, and they're estimating so many parameters that I just have no idea where ultimately the estimates come from. I don't think anyone knows. It's untractable, and I think that's a big problem. And I think this is comparatively tractable in terms of practice.
Thank you.
There's no other. Shall we let Marco relax?
All right, let's give. I'd like to give him another thank you for joining us.